Welcome to the deep dive. Today we're taking a shortcut right into the heart of organic chemistry.
Yes, specifically Chapter 11 of Clayden, Greeves, and Warren's Organic Chemistry, the second edition.
Exactly. You've sent us your notes, your sources from this chapter,
Sure.
and, well, our mission is basically to distill the really important concepts for you.
Focusing on that mechanistic reasoning, right? Reaction pathways, functional groups.
Functional group transformations, stereochemistry, and, those early ideas about retrosynthetic analysis. We're aiming to make these dense ideas crystal clear.
Give you those aha moments without getting too bogged down.
That's the plan. Okay, let's unpack this. So in our previous deep dives, we've talked a lot about nucleophilic attack on carbonyls where, a leaving group gets substituted. Standard stuff.
Right, like in Chapter 10.
But what happens when the carbonyl oxygen itself is the one that leaves? That's the surprising twist this chapter dives into, isn't it?
It really is. And what's fascinating, I think, is how reactions that seem pretty different on the surface, like making imines or acetals, they actually share this fundamental mechanism. It's still nucleophilic substitution at CO, but the big outcome is losing that original carbonyl oxygen.
So it connects back.
Absolutely. It builds directly on things like nucleophilic attack from Chapter 6, that substitution stuff from Chapter 10, and even acidity concepts from Chapter 8. They all kind of come together here.
Okay, interesting. So let's jump right into the first big example then. Forming hemiacetals and then acetals.
Okay.
Imagine you're in the lab, right? You mix acetaldehyde with methanol.
Right.
You're watching the IR, and the carbonyl peak, poof, it just disappears.
Yeah.
But you try to isolate a product, and you just can't seem to get anything stable. What's going on?
Yes, the classic hemiacetal situation. Most of them are, well, pretty unstable. They exist in this dynamic equilibrium with the starting aldehyde and the alcohol.
Like equilibrium, right?
Yeah, and for something simple like acetaldehyde with methanol, the equilibrium constant, K, is maybe around 0.5. Not great.
So it's mostly starting material.
Well, it means you need a lot of alcohol, maybe even use it as the solvent, just to push it towards the hemiacetal side. But even then, try to purify it.
It falls apart.
It just reverts back. It's more of a fleeting, intermediate, not usually a stable, isolable product on its own.
And this equilibrium, it's generally quite slow by itself, isn't it? How do chemists actually speed this up?
Precisely. It can be really slow, but you can speed it up significantly with catalysis. Either acid or base works.
Okay, how do they work differently?
Well, with acid catalysis, the acid protonates the carbonyl oxygen first. That makes the carbon atom way more electrophilic, pulls electron density away.
Makes it more attractive to the alcohol.
Exactly, more receptive to the nucleophilic attack by the alcohol. And that protonation is reversible. That's key.
Okay, and base.
Base catalysis works the other way around. The base snatches a proton off the alcohol's OH group first before it attacks.
Making a stronger nucleophile.
Right, you get an alkoxide ion, which is much more reactive, much more eager to attack the carbonyl. But here's an important point.
Yeah.
These catalysts, acid or base, they only increase the rate of getting to equilibrium. They don't change the position of the equilibrium itself. The hemiacetal is still fundamentally kind of unstable.
Got it. So they just make it happen faster, back and forth.
Exactly.
All right, so hemiacetals are tricky, often unstable intermediates, but then we make this jump to full acetals. And these are stable, isolable products. What's the secret here? What changes?
The big difference, the key distinction, is that forming a full acetal exclusively requires acid catalysis. No base catalysis for this step.
Only acid. Why is that?
Because think about the hemiacetal you just formed. It has an OH group. To get to the acetal, that OH group has to leave as water.
And OH is a bad leaving group.
Generally, yes. So you need to protonate it with acid to turn it into a good leaving group water, H2O. Base catalysis can't do that.
Okay, that makes sense. So what does the mechanism look like then, going from hemiacetal to acetal?
It's basically a two-stage process, and both stages involve these positively charged oxygen intermediates. First, the acid protonates the hemiacetal's OH group.
Making it ready to leave.
Right. Water leaves, and what's left behind is this really reactive species called an oxonium ion. It's got a positive charge on the oxygen, double bonded to carbon, highly electrophilic.
The oxonium ion, got it.
That's stage one. Then, for stage two, a second molecule of the alcohol comes in and attacks that electrophilic oxonium ion.
Attacks the carbon.
Attacks the carbon, yes. Then there's a final deprotonation step, losing a proton, and dingo, you get your stable neutral acetal, 2 additions of alcohol, loss of water, all acid catalyzed.
Right, so that oxonium ion is really the key intermediate driving it forward.
It really is.
Okay, so if we actually want to make acetals in the lab and, get a good yield, especially since that equilibrium might still not be fantastic, how do we push it? How do we force it to make the product?
Good question. It's all about controlling that equilibrium because every step is reversible. Two main strategies. You can use a huge excess of the alcohol.
Just swamp it.
Yeah, push it by Le Chatelier's principle. Or, more commonly and often more effectively, you actively remove the water as it's formed.
How do you do that?
Often by distillation. There's a special piece of glassware called a Dean-Stark trap, or Dean-Stark head, that's designed specifically for this. It collects the water as it distills off with an immiscible solvent, preventing it from going back into the reaction.
Clever. What about catalysts?
Yeah, you still need that acid catalyst, often something like toluene sulfonic acid, TSOH, chemists usually call it, or even dry HCl gas sometimes. For trickier cases like making acetals from ketones, which is harder, people sometimes use molecular sieves.
Molecular sieves.
Yeah, they're like tiny porous materials that selectively absorb water molecules, trapping them away from the reaction mixture.
Huh. Okay, so we've made them. What about breaking them apart? How stable are they?
And this is where they become super useful in synthesis. Acetals are remarkably stable towards bases. You can hit them with strong bases, Grignard reagents, other nucleophiles, and they generally won't react.
Okay, stable to base.
But put them in aqueous acid, even dilute acid, and they hydrolyze right back to the starting carbonyl compound and the alcohol. It's the exact reverse of their formation.
So stable to base, reactive to acid.
Precisely. And that selective reactivity is gold in organic synthesis. Oh, and cyclic acetals, like the ones you form using a diol, like ethylene glycol. They're often even more stable and easier to form.
Dioxylenes, right?
Exactly, dioxylenes. Partly due to entropy, which we'll probably touch on more in Chapter 12.
Okay, so it's stepping back again. What's the big picture here? Why is this stability profile so important for, practical chemistry, for modifying reactivity?
It makes them fantastic protecting groups. That's the key application. Imagine you've got a molecule with, say, a ketone group, but you need to do a reaction elsewhere using a reagent that would also attack the ketone, like a Grignard reagent.
Right, the Grignard would mess up the ketone.
Exactly. So what you do is you first protect the ketone by converting it into an acetal. The acetal doesn't react with the Grignard.
It's hidden, masked.
Precisely. Then you do your Grignard reaction on the other part of the molecule. Once that's done, you just add some dilute aqueous acid.
And pop. The ketone comes back.
The acetal hydrolyzes, and you get your original ketone back unharmed. It's a really elegant strategy.
That is clever. Any connection to nature here?
Oh, absolutely. Acetals and hemiacetals are everywhere in biochemistry. Think about sugars. Glucose, for example, mostly exists as a stable cyclic hemiacetal.
Or the ring form.
And when you link sugars together, like in maltose, a disaccharide, or starch and cellulose polysaccharides, those linkages are acetal linkages. They're called glycosidic bonds. So yeah, fundamental stuff.
Very cool. Okay, let's pivot from oxygen to nitrogen now. What happens when imines react with carbonyl compounds? We're talking about making amines, right? The nitrogen versions of carbonyls.
Exactly, amines. The reaction starts similarly, actually. The amines nitrogen, being nucleophilic, attacks the carbonyl carbon.
Just as the alcohol did.
Just like the alcohol. And this forms an intermediate called a hemiaminal, directly analogous to a hemiacetal.
Hemiaminal? Okay. Stable.
Usually not very stable,
Yeah.
like hemiacetals. But interestingly, this first step, the enamine attack, typically doesn't need acid catalysis. In fact, adding too much acid at this stage can actually slow it down.
Why is that?
Because acid would protonate the amine, the nucleophile, and a protonated amine, RNH3 plus SACA, isn't nucleophilic anymore.
Kills the nucleophile. Right. So the first step is okay without acid. What about forming the actual imine double bond?
That's the crucial second step, dehydration. Getting rid of water from the hemiaminal to form the CN double bond of the imine. And this step does require acid catalysis.
Same reason as acetals. You need to protonate the OH.
Exactly the same reason. You need to protonate the hydroxyl group on the hemiaminal to make it a good leaving group, water.
And the intermediate here, is there an equivalent to the oxonium ion?
Yes. When water leaves, you form an iminium ion, that's C double bonded to N, with a positive charge, usually on the nitrogen. It's the nitrogen analog of the oxonium ion. Very electrophilic.
Iminium ion. Okay, so if you need acid for the second step, but too much acid kills the first step.
You've hit on a key point. Amine formation is a classic example of a reaction that has an optimal pH range, usually somewhere around pH 4 to 6.
A balancing act.
Totally. Too acidic, low pH, and you protonate all your amine, stopping the first step, too basic, high pH, and you don't have enough acid to catalyze the dehydration step effectively.
Interesting. Like biological systems often need specific pHs.
Very similar principle, yes. Many enzyme-catalyzed reactions operate in narrow pH windows for maximum efficiency.
Okay, so we've formed an amine. Are they generally stable compounds?
Generally, simple amines are somewhat unstable, especially towards water and acid. They readily hydrolyze back to the carbonyl and amine. It's the reverse of their formation.
So like acetals, you often have to remove water during synthesis.
Yes, often using similar techniques like a Dean-Stark trap to drive the equilibrium towards the amine product. However, some types of amines are significantly more stable.
That's
things like oximes from hydroxylamine, hydrazones from hydrazine derivatives, and semicarbazones from semicarbazide. These have an electronegative atom attached to the amine nitrogen.
And why does that make them more stable?
It allows for electron delocalization, sort of spreading out the electron density of the CMN bond. This makes the carbon less electrophilic and the imine less susceptible to hydrolysis. Historically, these stable derivatives were really important.
How so?
They're often crystalline solids with sharp, characteristic melting points. So before modern spectroscopy like NMR became routine, chemists would make these derivatives to help identify unknown aldehydes and ketones.
For characterization. Now we just use NMR mostly.
Pretty much, yeah. NMR is usually faster and gives more information.
Okay, you mentioned iminium ions for imines, and we talked about oxonium ions for acetals. How do they really compare? Are they basically the same kind of intermediate?
They're very closely related. Both are formed by loss of water. Both are highly electrophilic intermediates with a positive charge involving the heteroatom, oxygen, or nitrogen.
So what's the key difference in their fate?
The main divergence is what happens next. The iminium ion typically has a proton on the nitrogen atom, an NH proton. Losing this proton gives you the neutral, stable imine.
Right, deprotonation.
Whereas the oxonium ion formed on the way to an acetal usually doesn't have a proton it can easily lose to become neutral. Instead, its electrophilic carbon gets attacked by that second molecule of alcohol to form the acetal.
So binium deprotonates to amina. Oxonium gets attacked to form acetal.
That's the key difference in their typical reaction pathways, exactly.
Okay, that clarifies things. But what if the amine you start with is secondary, like R2NH? It reacts, forms the hemiaminal, then the iminium ion. But now there's no NH proton to lose.
Excellent question. What happens then?
Yeah, what's the product?
This leads to a different type of product called an enamine. Since the iminium ion formed from a secondary amine can't lose a proton from nitrogen.
It loses one from somewhere else.
Exactly. It loses a proton from the carbon atom next to the CMN bond, the alpha carbon. This forms a carbon-carbon double bond adjacent to the nitrogen.
CH next to N. N for the double bond, M for the nitrogen, enamine.
You got it. It's basically the nitrogen analog of forming an enol or enolate from a carbonyl. We'll see more parallels later. And like imines, enamines are generally unstable towards aqueous acid.
Interesting. Okay, so we have these iminium ions, highly electrophilic. How do chemists actually use this reactivity in synthesis? What's the killer app?
Probably the most important application, a real workhorse reaction, is reductive amination. It's an incredibly useful way to make amines.
Reductive amination, how does it work?
It cleverly combines imine or iminium ion formation and reduction in one process, often in the same pot. You react a carbonyl compound with an imine.
To make the imine or iminium ion?
Right, in situ. And then you immediately reduce that CN bond to a CN single bond using a reducing agent.
What kind of reducing agent? Does that have to be special?
It usually is, yes. The beauty often lies in using mild selective reducing agents. A very common one is sodium cyanoborohydride, NaBH3CN.
Sodium cyanoborohydride. Why that one?
Because it's selective. It's strong enough to reduce the highly electrophilic iminium ion, but it's generally not strong enough to reduce the starting aldehyde or ketone or even the neutral ion itself.
So it waits for the iminium ion to form, then reacts.
Pretty much. This selectivity allows you to just mix the carbonyl, the amine, and the NaBH3CN together, maybe adjust the pH slightly, and cleanly get the amine product.
Very efficient. And you can make different kinds of amines.
Absolutely. Use ammonia, you get primary amines. Use a primary amine, you get secondary amines. Use a secondary amine.
Yeah, get tertiary amine.
Exactly. It's very versatile.
And connections to nature again.
Oh, big time. Nature does reductive amination constantly. Synthesizing amino acids from alpha-keto acids is a prime example, often involving vitamin B6 derivatives. Biochemists often call the amines involved here Schiff bases. Nature's been doing this way longer than we have.
Shift bases, right. Okay, any other cool reactions involving these iminium ions?
Yeah, a couple more important ones. Cyanide ion, CN, is a good nucleophile. It can attack iminium ions too.
What does that lead to?
It forms an alpha-aminonitrile, and these alpha-aminonitriles can then be hydrolyzed, usually with acid, to give alpha-amino acids.
Amino acids, so you can make amino acids this way.
Yes. This whole sequence is called the Strecker synthesis. It's a classic, powerful lab method for making amino acids, especially ones that aren't the standard 20 proteinogenic ones.
The Strecker synthesis. Okay. Anything else?
Well, strong reducing agents like lithium aluminum hydride, LiH4, can reduce amides and nitriles all the way down to amines, and the mechanisms often involve aminium-like intermediates along the way.
So iminium ions pop up in various reductions too.
They do. And think about complex molecule synthesis. There's a great example in the textbook, synthesizing a spider toxin, I believe. Reductive amination is used strategically there to connect different fragments of the molecule together.
Building complexity.
Exactly. And of course, protecting groups, like the acetals we discussed, are often crucial in these multi-step syntheses to make sure only the desired reactions happen.
Right, protecting groups are key. Okay, one final major transformation from this chapter. The Wittig reaction. This one seems really different.
It is quite different, yeah.
Instead of swapping the oxygen for another oxygen or a nitrogen, the Wittig reaction replaces the entire carbon-oxygen double bond with a carbon-carbon double bond.
Yeah.
CO becomes CC. How does that work?
It's a really ingenious reaction. It involves reacting a carbonyl compound, an aldehyde or ketone, with a special reagent called a phosphonium ylide.
Phosphonium ylide. What on earth is that?
An ylide, pronounced I-L-ade, is a neutral molecule, but with formal positive and negative charges on adjacent atoms. In this case, it's usually negative charge on carbon right next to a positively charged phosphorus atom.
Okay. Adjacent plus and minus charges. How do you make them?
You typically make them in two steps. First, react a phosphine, like triphenylphosphine, PPH3, with an alkyl halide. That gives you a phosphonium salt. Phosphorus is positive.
PPH3 attacks RX.
Okay. Then you treat that phosphonium salt with a really strong base, like butyllithium or sodium hydride. The base pulls off a proton from the carbon next to the phosphorus, creating that negatively charged carbon right next to the positive phosphorus. That's your lilid.
Strong base needed. Got it. So you mix this lilid with a ketone or aldehyde. Then what? The mechanism sounds unique.
It is. It's totally different from the acetyl or imamine stuff. The negatively charged carbon of the ylide acts as a nucleophile and attacks the carbonyl carbon.
Okay, standard nucleophilic attack so far.
Right. This forms an intermediate called a butane, which has the negative oxygen and the positive phosphorus in the same molecule, but separated by a couple of bonds. But this often quickly cyclises.
It forms a ring.
Forms a four-membered ring containing phosphorus and oxygen. This is called an oxyphosphatane. It's got a PO bond, a CC bond, a PC bond, and an OC bond in a square, usually unstable.
Oxyphosphatane. Okay, four-membered ring. Then what?
This is the crucial part. That oxyphosphatane spontaneously collapses. It breaks apart in a specific way. It breaks the PC and the OC bonds that were part of the original lid and carbonyl, respectively. And simultaneously, it forms two new double bonds. The CAC bond of your desired alkene product.
The goal.
And critically, a phosphorus-oxygen double bond, PO, forming phosphine oxide, usually triphenyl phosphine oxide, PH3PPO.
PH3PO, why is that so important?
Because the phosphorus-oxygen double bond is incredibly strong, like thermodynamically super stable. One of the strongest double bonds known, around 585 kilojoules per mole.
Wow.
That massive stability, the formation of that super strong PO bond, is the thermodynamic driving force for the entire reaction. It just pulls the whole thing towards product.
So it's not an equilibrium problem like acetals.
Nope. The formation of that PO bond makes the Wittig reaction essentially irreversible and highly efficient. It just goes. It's a fantastic way to make alkene.
That's really neat. A totally different strategy driven by that PO bond formation.
Exactly. It's a cornerstone of alkene synthesis.
Wow. Okay, what a deep dive that was into the real versatility of carbonyl compounds and all these clever ways chemists and nature, too, have figured out to transform them.
It really was. We've seen how swapping out that carbonyl oxygen, whether it's for another oxygen to get acetals or nitrogen for imines and enamines.
Or even swapping the whole CO for a CC in the Wittig.
Right. It just opens up this huge landscape of synthetic possibilities.
And if we connect this to the bigger picture, What's the main takeaway?
I think it really highlights a core principle of organic chemistry.
Hmm.
Understanding the mechanism, understanding how these key intermediates like oxonium ions and iminium ions form and react. That's what lets us predict what will happen, design new reactions, and control outcomes.
It shows how just, small changes in conditions or reagents can lead to completely different products.
Exactly. Different but equally useful and powerful outcomes. It's really quite elegant.
Yeah, from those vital protecting groups and complex synthesis, right through to the actual building blocks of life like sugars and amino acids. These reactions really are everywhere once you start looking for them.
They truly are. It showcases the adaptability and, well, the beauty of organic chemistry.
We really hope this deep dive into Chapter 11 has sparked some of those aha moments for you and given you a solid footing for understanding these absolutely crucial reactions.
Hopefully connect some dots.
Now, as always, something for you to mull on. We saw how nature uses reductive amination, with incredible efficiency and specificity for making amino acids. Thinking about that, what other complex protecting group strategies, or maybe totally novel, super mild catalytic processes might nature be using that we haven't fully figured out or harnessed yet for our own lab syntheses?
That's a good one. Lots to potentially uncover there.
Definitely something to think about. Thank you for being part of the Last Minute Lecture family.